All right, welcome back again, everybody. Today we're going to be moving on to section 8.3, and today we're going to be talking about physics and engineering applications. Let me get some things pulled up, and we'll start in just a moment here. There we go. All right. Okay, so a couple of things I want to say. This section is a little bit of a long one, so a bit of fair warning there. Anytime you've got a section that involves applications, they tend to be long. I also generally tend not to emphasize these application sections on my tests because, frankly, for the physicists and the engineers out there, this is what you're going to spend all of your upper division major courses doing. So if you want to get a degree in engineering and physics, it's going to be applications of the mathematics. So this is a math class, and I'm a mathematician, so I tend to like to emphasize the math more than I do the applications to specific things like that. But if you really, really enjoy this section, which I hope some of or many of you do, this is the kind of stuff that you can do in a physics and an engineering class. All right, so we're only going to cover a couple of applications. That's another thing I got to mention. There are multiple application sections for this chapter, and we only do this one, which is basically physics and engineering. So we're going to talk about hydrostatic pressure and force. Then we're going to talk about moments and centers of mass, basically engineering and physics, right? However, if you are interested in applications of integration to economics and biology, that is section 8.4, which sadly we will not be covering. And even more interesting to me is actually section 8.5, which is an application to probability. So any of you that want to go into stats or you want to learn probability, or maybe you want to be like a risk analyst or um, like an actuary, things like that, I would recommend just kind of skimming through this section and reading up a little bit about probability. You'll definitely have to take a course in probability and stats that involves calculus if you want to become an actuary or a risk analyst. But if you're interested, it's there. This is actually another reason why I actually recommend that people wait until they've taken calculus before they do statistics and probability, because all of the meaningful statistics and all the meaningful probability really requires calculus concepts because you want to add up a bunch of stuff, right? You want to basically construct functions and integrate them, and that will give you probabilities. All right, so starting with hydrostatic pressure and force, we're going to develop the basic theory, and then we're going to get a formula for how to compute these things. So let's get started. Here's the setup. We're going to suppose that there is a thin horizontal plate with area A, and that it's submerged in some fluid to a depth of d meters. All right, so imagine you've got literally like a metal plate or some thin plate in some water that's submerged to a depth of d meters. In a fluid of density rho times, I'm sorry, not times, rho kilograms per meters cubed. This is the Greek letter rho. It's kind of like the Greek letter r, and it's a common use for a density function. So a lot of times density will be represented by rho. All right, now the fluid above this plate has a volume. So you can imagine let me do this. Imagine there's a column of water or whatever the fluid is. There's a column of water above that thin plate, and the volume of that water is the area of the plate times the depth. So very intuitively, the literal volume of that column of water is the area of this base times how deep down it is. And so now that we know the volume and we know the density, we can compute the mass. So the mass is density times volume, so you get rho v. And since v is AD, we get rho AD. So using the formula F equals ma, we can compute the force exerted on the plate from this column of water. It's F equals ma, where m is the mass and a is the acceleration. In our case, the acceleration is just given by the gravitational constant g. And so our formula becomes rho AdG. Yeah, g is the acceleration due to gravity. For one thing, I'll say this, you can just leave it at g, and you should leave it at g until like the very last moment that you possibly can, because then you can start to plug in numbers, but it's nice when you have a general formula as long as possible. All right, now what is the hydrostatic pressure? So hydrostatic pressure on the plate is defined as the force per unit area. That's what pressure is. It's basically how much force is being exerted on each piece of area, per unit area. So pressure P is force divided by the area. We calculated the formula for the force. The area is given by A, and so the pressure is given by rho GD. Rho GD. So pressure is measured in pascals, which is newtons per square meter. Oftentimes we use kilopascals or kPa. Another important bit, this is where the physics comes in. It's been experimentally verified that at any point in a liquid, the pressure is the same in all directions. So a good example is that a scuba diver will feel the same pressure on their ears as they will their nose. So the pressure does not change from any direction. The pressure is the same in all directions at any given point, So that means that the pressure in any direction at a depth d in a fluid of density rho is given by this equation. So this is the equation for the pressure. All right? Okay. Now, let's apply this idea to an example with a dam. So one thing I'll say is this is the basic formula, rho GD. Now we just need to use that formula to construct our integral. So this is very similar to what we did in the last couple sections where we get a formula that we want to add up, and then we figure out the details of that formula, and then we add it all up, right? It's that same thing. So here's the setup. Let's say the cross section of a dam has the shape of a trapezoid. The height of the dam is 20 meters. The width at the top is 50 meters, and the width at the bottom is 30 meters. Let's find the force on the dam due to hydrostatic pressure if the water level is 4 meters from the top of the dam. So that's the goal here. We want to find the force on the dam due to the hydrostatic pressure, because basically all this water is applying pressure is applying pressure to the dam, right? And so we want to find the force on the dam due to that pressure. All right. So again, thinking about the mechanics of the Riemann integral, we're going to figure out how much force is exerted on a single slab of water, and then we're going to use integration to find the total hydrostatic force. All right. So we get to choose a coordinate system. This is one of the things that's a little bit tricky about physics application problems or engineering problems, is that you get to choose a coordinate system. And the choice really is yours, but once you choose it, you have to stick with it. And if you choose a coordinate system that is different from your partner's coordinate system, then your calculations will differ, but your end result should be the same. So this is one time where I'll re-emphasize that you want to make sure that you write down your work clearly and cleanly and neatly so that everyone can follow exactly your line of reasoning, because we won't actually know if you're right if we can't follow that calculation. So make sure that you're keeping your calculations well written and well organized. Okay, so what we're going to do for our setup is we're going to choose a vertical x-axis. All right, we're choosing a vertical x-axis, and we're going to put the origin at the surface of the water. So right here, this is the origin for us, and we're going to let the positive direction be downward. So here's our origin, and this is the positive x-axis. All right, so try to let that settle in. There we go. Okay, now at this point, the water is 16 meters deep. So this length right here is 16 meters because the total height of the dam was 20 and 4 from the top. That was in the previous slide. Okay, so now here's basically the picture. Here's the setup. We need to find the hydrostatic force exerted on this slab of water, just like so. And how do we do it? Well, we're going to break things into pieces, and because we've got triangles involved, we're going to use similar triangles. Couple things, this is going to be the length, delta x sub I star, where that end point is chosen somewhere in this interval of length delta x. And then we're going to put all the pieces together. All right, so let's see. If we want to know the hydrostatic force exerted on this slab of water, we're going to need to know its size. We're going to need to know its size. We know how far away it is from the surface of the water, so that's like d. That's the depth of the water. But we don't know the area of this thin rectangle here. We know some pieces of it, right? We know that since this length is, was it 30? Or wait, hold on. 50 meters altogether on the top, 50 meters. Oh, that's right. It was 30 meters down here. That's right, that's right. Okay, let me draw a couple extra lines here. Boop. So this will be 15 because we know that this total length is 30. And then this will be 10. So we know that this is 10, but the thing that we don't know is we don't know A. We don't know A, and A is this length right here, and A depends on x sub I star. So we need to find a formula for A in terms of x sub I star, which is our depth. So here we go. Using similar triangles again, we get this relationship, that this ratio, this over this, is equal to this over this. That's this equation right here. And that's the result from geometry about similar triangles. Now, from this equation, we can solve for A, and we get that A is equal to this, which we can then simplify to be this formula right here. Great, so now we know what A is, and so now we can determine the width of that slab. The width is going to be 2 times 15 plus A. That's given by this picture here. The width is, let me clear some things. All right, so what's the width? The width is going to be 15 plus A twice. That's where we're getting this. 15 plus A twice. Now we've got a formula for A. We plug it in, simplify the result, and we get 46 minus x sub I star. Sweet. Okay, so now we know the width. We have the total width of that slab, and because the what do I want to say, width or height of the slab is delta x, we now know the area of the slab. So the area is w sub I times delta x, which is that times delta x. All right, so I'm going to throw up the thinker for just a minute. I want you to sit here and ponder that. Make sure that you're comfortable with where all of these pieces are coming from. Make sure that you're comfortable with this picture and what all those pieces are representing, and then I'll move forward in just a moment. All right, let's move forward now. Okay, now if delta x is really, really small, the pressure on that strip is given by this, 1000 g times x sub I. The 1000 is coming from the density of the water. G is the gravitational constant, and x sub I is the depth. So remember the formula for pressure? Hold on, let me use this. The formula for pressure was rho g d. That's what's going on right here. And if delta x is small, then the pressure is going to be approximately this bit right here, that bit right there. Oh, yeah, also the pressure is equal in all directions, so we're only concerned about area here, not volume. We don't need to think about we don't need to think about what's going on behind this picture. We don't need to think about this piece, because the pressure will be the same. The pressure will be the same. Okay, so what is the hydrostatic force? The hydrostatic force is the force, it's the pressure times the area. So the force on each one of those slabs is the pressure on each one of those slabs times the area. And actually, you know what? That should say A sub I. Real quick, little, oops. A sub I, there we go. Yeah, it's A sub I, exactly, because the area depends on x sub I star. Okay, so the force is pressure times area. So we get our formulas. There's, pressure times air. Oh, no, wait, sorry. I have it broken up into pieces. Let me try to highlight the pieces. Okay, where did it go? The area is this, and then this is the pressure. Okay, so I didn't have it broken up. See, this is why you want to pause sometimes and think about, like, wait, what am I actually looking at? I encourage you to do that, because if you're not making sense of what each piece is, then everything starts to fall apart later on. So do take the time to pause, ask your neighbor, ask your partner, ask your dog if you have no one else to talk to, or just the wall. But it's good to stop and make sense of each little piece. Okay, so that's our pressure, that's our area. Now we know the force. Now we just need to add it all up, right? Add it all up. So if we add up all the forces and then we let the height of those little slabs go to 0, In other words, take the number of slabs to infinity, then we get that the force is equal to the limit of this sum. But again, that's the Riemann integral. That is the integral by definition. So we're going to be integrating from 0 to 16 because the water has a depth of 16. 1000 gx times 46 minus x. We can pull out all the constants. So I pulled out 1000. I changed g to 9.8 because we're working on the planet Earth, presumably. And then now we have a very simple integral to evaluate. So when you see something like this is where you should feel like a breath of relief because you're like, oh, that's an integral that I can do. All of the mess has been moved out of the picture and we're just doing a basic calculation. Apply FTC2, we get these antiderivatives, evaluate from 0 to 16, go to your calculator, do some calculations, and you get this. There we go. So 4.43 times 10 to the 7th newtons. That's the total force on the dam. Cool stuff, huh? All right. Okay, so that's it for hydrostatic pressure and force. Now let's talk a bit about moments and centers of mass. And what's kind of cool is that at the end of this part of the section, we'll talk about the theorem of Pappus, or the theorems of Pappus, and how those were showing up in the last section as well. Okay, so here's the idea for this part of the section. In this part of the section, we are basically looking for the point on a thin plate where you could balance the plate horizontally. So, just imagine you had like your phone or something, and the question is, where would you put your finger so that you could balance it on your finger? I can't do it. That's basically what you're looking for. So where is that exact point? Find where that exact point is. Except now where it gets interesting is the plate can be all sorts of different shapes. It doesn't have to be a rectangle or a square. It could be anything. It could be any like region, right? So how do you find the point in that region where you can balance it on your finger? That's the question. Okay, so in one dimension, this is basically like balancing a stick on your finger. So if you think about trying to balance your pencil, which I'm sure many of you have done before, where you try to find where to balance it, right? And you take a bit of time. Oh, I almost got it. There we go. Okay, so where is that point? That's the question. Well, the answer to that question has been known for quite a long time. Archimedes discovered an astounding relationship between masses and distances that tell you precisely where that point is going to be. And this is what's called the law of the lever. So you might remember this vaguely from a physics class if you took physics back in high school or something, but if you don't, that's okay. We're going to review it here and talk about what this means, and this is going to help us find the center of mass. So let's say we have two masses, m1 and m2, and they're attached to a rod of negligible mass. So here's a mass, and we're going to say that this rod has basically no mass, maybe a tiny, tiny bit of mass. And we're going to put these masses at a distance d1 and d2 from a fulcrum. A fulcrum is that pivot point on a lever. Then what Archimedes was able to prove is that the rod will only balance if this equation holds true, if you have this relationship between the masses and the distances. So this pencil will only balance on my finger if the mass over here, the mass over here, the distance here are related by this equation. So m1 times that distance d1 is equal to m2 times that distance d2. That's the law of the lever. Okay, now we're going to mathematize this a little bit. So what we're going to do is we're going to put that fulcrum, or I should say this, we're going to put our rod on the x-axis. We're going to put the rod on the x-axis just like what's pictured here. Oop, let me get my laser pointer back. There we go. Yes, okay, and what we're going to do is we're going to put mass 1 at the point x1, and we're going to put mass 2 at the point x2, right? And now this fulcrum is going to lie here at this point, and we're just going to label that point x bar, wink, wink, wink. Why am I winking? Because that's actually the center of mass. So that's going to be the center of this mass system, you could say, the center of the system. Now the law of the lever yields that this relationship has to hold. So m1 d1 equals m2 d2. we can express the distance d1 as this difference, x bar minus x1, right here. And we can express the distance d2 as x2 minus x bar, right here. Now we're going to do a little bit of algebraic massage, and we'll be able to solve for the center of mass. So we distribute the m1, we distribute the m2. We're going to get all the terms that have x bar together on one side. Now we can factor out that x bar, and we get this. Divide both sides by m1 plus m2, and we get a formula for our center of mass. There it is. That's the formula for the center of mass. Putting it all together, let's get the actual definition. So the numbers m1, x1, and m2, x2 are called the moments of the system, the moments about the origin. So let me flash back real quick, right? Remember our system is anchored right here. So there's the origin. And x1 is this distance. And x2 is this distance. So once you choose an origin, once you choose a coordinate system, you're going to express everything in terms of that coordinate system. So m1 times that distance x1 and m2 times that distance x2 are called the moments of the system. All right? And this equation gives you the equation of the center of mass. So what this is saying is that the center of mass of the system is obtained by adding the moments of the system and dividing by the total mass. So m1 plus m2 is the total mass of the system. And that's really what it's saying. Yeah, and that's about it. Okay. All right, so now that's if you just have two masses, right? Two masses, and we're still dealing with just one dimension, so we're placing these two masses on the x-axis on a line. All right, you can generalize this. You can generalize this to having a whole bunch of masses that are placed along a line. So that's what we're going to do here. Suppose we've got a system of n particles, and here are the masses of those particles, m1, m2, m3, m4, all the way up to mn. And we're going to locate these masses at the points x1, x2, oops, this should say xn. There we go, I'll fix that later. Located at all these points on the x-axis. Then the center of mass is going to be just a generalization of the formula we saw a moment ago. It'll be adding up all the moments and then dividing by the sum of all the masses, which is the total mass. There you go. So capital M is the sum of all the moments. Little m is the total mass of the system. And capital M here is actually what's called the moment of the system about the origin. So the moment of the whole system. Another thing that's cool, this equation right here, you can rewrite it as capital M equals little m times x, which basically says that if the total mass of the system were concentrated at the center of mass, then the moment at the center of mass is the same as the moment of the system. All right, so this is another time where I'm going to throw the thinker up for a minute, and I want you to just ponder these ideas for a couple minutes. You can flash back a couple slides and look at the arguments again if you'd like. Talk to your physicist friends, talk to your engineering friends. They can shed some light, but just take a minute to let this digest. Okay, now let's continue. That's right. Okay, so now let's talk about two-dimensional systems. Now things are getting a little more interesting. Suppose we've got a system of n particles again, and they've got masses m1, m2, dot, 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 all the way up to mn. But now we're going to locate those masses at points on the plane. They're located here, here, dot, 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 here. So you've got all these point masses all over the plane, and we want to find, frankly, the center of mass of that. Well, now, because we're in two dimensions, we're going to have two different moments. We're going to have the moment of the system about the y-axis and the moment of the system about the x-axis. There we go. Now, I want to pause here for a minute because I want to point out that the moment of the system about the y-axis is equal to these moments. And what I want to point out here is that we're multiplying the mass times x. And the reason for that is because this gives you the distance from the y-axis. Let me draw a quick sketch here. right? So let's say we've got this point right here, x1, y1, and we've got a mass 1 at that point. If we want to know the moment about the y-axis, then the distance we're going to measure is this distance right here, because this is the y-axis and this is the x-axis. So the moment of the system about the y-axis means we need to look at these x distances, right? That's why these are coming in. So if you want to talk about, let's say, spinning things around the y-axis, you're going to look at x distances. Now, maybe in a flipped version, if you want to look at the moment of the system about actually wait, I'll leave that there. The moment of the system about the x-axis, now you're going to be looking at these distances instead, y1, and that's why these are coming in. All right. So the moment depends on which axis you're referring to. Moment of the system about the x-axis, you're going to add up y values, or m masses times y values. Moment of the system about the y-axis, you're going to add up masses times x values. All right, and then think about this picture, and if you can think about that picture, that'll help you remember what the moments are. Okay, one way that I try to think of it is you can almost think about these these terms right here, mi, xi, as the influence that mass has on the system with respect to whichever axis you're referring to. It's kind of like if you had a mass that's really, really close to an axis, the effect that mass has is going to be different than if you had a mass that was really, really far away from the x-axis, right? So it's kind of like the influence they have on the system. I don't know if that helps, but that's one of the ways I think of it. All right, so now we can talk about the moment about the y-axis, the moment about the x-axis. Let's find a couple numerically, and this is one I want you all to actually try. All right, so try to do this one on your own, and then we'll do it together. Think about it. Find the moments and center of mass of the system of objects that have masses 3, 4, and 8 at the points -1, 1, 2, -1, and 3, 2, respectively. Okay, one way to get started is to say something out loud. So if you're stuck for a minute, say something out loud about what you could start with. Maybe something about moments or the formulas for moments. Say something out loud. All right, and now try to calculate it on your own. See if you can compute the moments and then the center of mass. All right, now let's do it together. Okay, so for one, if we want to find the moments, well, you know what? I think a picture would help me a lot here. I don't know about you, but sometimes pictures just reveal enough that they're just nice and helpful. Okay, so let me do this. Let me do this. Okay, here's x. Here's y. Okay, we'll say -1 and 1. And I'll put a mass right here. So this has mass 3. That's our first mass. Okay, then we'll do 1, 2, and then -1. All right, so this one right here, this has mass 4. And then the next one is at 3, 2. So we've got another mass right here. And that's mass 8. Okay, so one reason I like to do this is because this helps me think about directions and which distances I'm going to be taking, but it also helps me make sense of what I'm looking for. Because if I'm looking for the center of mass, I'm looking for the point in here where I could balance these three masses if they were just on the plane. So if I could put my finger somewhere on the plane, where would I put my finger so that it balances horizontally on my finger? And even just looking at this, maybe you can see that we're probably going to have to be a little bit closer to this one because the mass is heavier. So you can use your intuition for things like this. If there's a heavier mass, then usually you need to have your finger closer to that mass. So just at a glance, I suspect that my center of mass is going to be about here. This is just a guess, okay? Maybe I'll write down my guess and see how good it is later. I think it'll be right about here. Oops, sorry. X bar, Y bar, right? Center of mass in each direction. That's just my guess. No idea what it's going to be. Okay, so now the way that we do this is we use those formulas. We need to add up all of those moments and divide by the total mass. So here are the moments about the axes. This is the moment about the y-axis. It's the masses times their distances from the y-axis. So let's go back and look at that. So this distance from the y-axis, and then this distance from the y-axis, and then this distance from the y-axis. That's what's happening right here. Add all those up, you get 29. So that's the moment with respect to the y-axis. Now do the same thing for x. Mass, 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 distance, distance, distance. And on our picture, there, this distance, and this distance. All right, I really should say displacement. I really should say displacement and not distance. I tend to abuse those words a lot, but really they're the displacement, right? That's why you can have a negative value here. All right, now what's the total mass? The total mass is what you get when you add up all the masses. You get 15. So the center of mass with respect to the x coordinate of the center of mass is given by the moment with respect to the y-axis divided by the total mass. You get this. And the y coordinate of the center of mass is given by the moment with respect to the x-axis divided by the total mass, and you get 1. Okay, so the center of mass of this system is 29 over 15, comma 1. That's exactly where you would place your finger to balance the masses horizontally. One thing I'll say is that this right here, 29 over 15, is approximately 2. Yeah. It's approximately 2 because if 29 were 30, then you would have 30 divided by 15, which is 2. Now let's go back and look at our guess. Oh, pretty good. Pretty good guess, right? You see, I had it at x coordinate 2, y coordinate 1. I should have been a little bit higher up. So the actual coordinate of the center of mass is right here. And that's 29 over 15, comma 1. There we go. All right. Okay. All right, there we go. Okay, so now let's talk a bit about centroids. So now that we've seen this in 1 dimension, we've seen this in 2 dimensions, and we've seen it only discretely. So that's one thing. We haven't done this in a continuous way. Where's the calculus? We haven't really done any calculus yet. We've just been adding some things up. So that's what we're going to lead into next. So first, the start is the centroid of an object is considered the geometric center. So when people talk about a centroid, they're talking about the geometric center or the middle of the object. Now, if an object has uniform density, then the center of mass lies at the centroid. So in other words, if the density is constant, then the center of mass and the centroid coincide. So this is the distinction between the two. You can think of the centroid as a geometric center and the center of mass as a mass center. All right, there you go. And if it turns out that the density of the object is uniform, then they're at the same place. Generally speaking, well, I'll get to that part later. Okay. Here it is. This is exactly what I was going to say. So in this class, we will be assuming that the density of our regions is uniform. All right, so this is an important thing to recognize. Because of this, the centroid will always coincide with the center of mass in our cases. But in general, in fact, I would say more often than not, these things do not coincide, because more often than not, the density of the regions that we're interested in exploring is not uniform, right? It's not uniform. Even for something like a cell phone, right? Even like a phone, the density of this object is not uniform at all. It's got like pockets where there's more mass, pockets where there's less mass, and so the density is not uniform. So we are not going to be considering cases like that. We're going to be considering nice, straightforward, uniform density objects. All right. In practice, if the density is not uniform, then the density is described as a function of the points in the region. Basically, the density depends on where you are, right? So what you get is you get a density function, a function of x and y. You plug in the x coordinate, you plug in the y coordinate, and it'll tell you the density at that point. For us, because it's going to be uniform, we don't need to have it as an explicit function of x and y. We can just call it some number, uniform. All right? Okay. So before we can develop a more general formula for more general regions, we need a couple helpful propositions. The first one is called the symmetry principle. And I'll admit that these are intuitive propositions. So you can let your intuition about physics and the real world help you to at least believe that these could be true. So let's say you've got a region in the plane. If that region is symmetric about a line, L, then the centroid of that region must lie on that line. All right? So ponder that one for just a minute here, and then I'll elaborate. Okay, now let me elaborate a little bit with an example, for example. uh, okay, so this is saying that if your region has symmetry about a line, then the center of mass, or the centroid, must lie on that line. So think about like a triangle. We'll say like an isosceles triangle. Actually, let me draw it like this. Okay, isosceles triangle. What this theorem is saying is that the centroid of that region must lie on the line of symmetry somewhere. Actually, in this case, it'll be a little bit lower. That's what it's saying. So symmetry kind of cuts your work in half, you could say. Symmetry gives you an idea where things are going to be. It just cuts your work in half. That's really what it does. All right, so symmetry principle. We're going to use that in just a moment. Next, the moment of the union of two non-overlapping regions is equal to the sum of the moments of the individual regions. So this just says, hey, if you've got two non-overlapping regions like so, then the moment of the union is equal to the sum of the individual moments, as long as they're not overlapping. If they're overlapping, then you have to account for the overlap, and it gets a little bit more complicated. All right, but there's one that should also feel a little bit intuitive, so I want to throw the thinker up again and just ponder this for a minute before we move on. All right, so here's the setup. The goal here is we want to start with a region that looks roughly like this. So let's say we've got a region that is, say, the area under a curve. Wink, wink. We would like to be able to find the centroid of that region that is the area under that curve. So let's suppose that it's bounded by the curve y equals f of x and the x-axis and the lines a and b for now. And we want to find the centroid of that region. Well, this is going to sound very, very familiar. We're going to divide the interval a to b into subintervals of equal length, delta x. We're going to choose our sample point to be x sub I bar. We're going to choose the midpoint of each subinterval, and we're going to use that as our sample point. So x sub I bar, this point right here is what we're going to focus on right now, okay? So by the symmetry principle, we know that the centroid of one of these approximating rectangles has to lie on the vertical line of symmetry, and it has to lie on the horizontal line of symmetry by the symmetry principle. Maybe more intuitively, if you've got a uniform density rectangle that you try to balance, on your finger is going to be right in the middle. Okay. All right, so where is this point exactly? That point is at the coordinates x sub I bar, the midpoint, and then 1/2 of f of x sub I bar. And I want to take a moment to just emphasize this coordinate right here. Remember that the height of these rectangles are given by the sample point. Given by the function evaluated at the sample point. So the height of this rectangle is f of x sub I bar. That's the height of that rectangle. Now, if we want to know where the midpoint of that line is, it's just the halfway point. And that's why we're getting 1/2. So the coordinates of that midpoint, I'm sorry, the coordinates of that centroid are x sub I bar and half of f of x sub I bar. All right? Okay, I hope that's not too bad. Now, the area, right? So now we have the actual point. We have the point itself. The area of each one of those rectangles is going to be very familiar. The area is the same thing we've seen before many times at this point. It's the height of the rectangle times the width of the rectangle. So that's the area of the rectangle. Now we know the area. If we want to know the mass of that rectangle, we need to multiply by its density. In our case, the density is some uniform number rho. It's just a constant rho. So the mass of each one of these rectangles, let me erase some stuff. Let me highlight this thing, right? So let's take a look at just this rectangle for a minute. The mass of that rectangle is given by this formula, rho times the area. Sweet. Now we know the centroid of this rectangle, and we know the mass of this rectangle, and that's how we're going to be able to find a bunch of stuff. A bunch of stuff. Here we go. All right, so first we can find the moment. So we know that the moment of this rectangle, I'm going to pop it out here again. All right, so what is the moment of that rectangle? It's the product of the mass and the distance from the centroid to the y-axis. That is the moment of the system. And that's just x sub I. So the distance is x sub I, and that's what I'm going to point out right here. So maybe I'll do it right here. X sub I bar, that's the distance of the centroid of this rectangle from the y-axis. So the moment of this rectangle with respect to the y-axis is given by the mass of the rectangle times its distance from the y-axis. When we simplify things, or I should say move things around to make it a little more meaningful, we get this. All right? Okay, and now what we're going to do is we're going to add all of those up. So if we want to find the moment of this region with respect to the y-axis, we're going to add up the moments of all of these non-overlapping rectangles. So this is where that second proposition comes in. We're going to add up all the moments of each one of these rectangles, and that's this piece right here. This is adding up the moments of all those rectangles. Just a reminder of the mechanics here. We've got the mass. Where is the mass coming from? It's coming from, oh, sorry, I moved things around a bit. Here's the area. So area times density gives you the mass. And then there's the distance from the y-axis. Add all of those up and you'll get an approximation of the moment. Then if you take the limit as n goes to infinity, or you shrink delta x to 0, you'll get the exact moment of the region, which is given by this formula right here. So take a look at the pieces again. Actually, let me go forward a minute. Yeah, okay, so take a look at the pieces again for just a moment, just a moment here, right? The moment of the region, the actual region, with respect to the y-axis, is given by the density of the region times this integral. And what's really cool here is that the integral makes sense. It makes sense if you look at the pieces, right? There's the distance from the y-axis. And there's the height. And there's the width. So it's quite literally area times distance from the y-axis times density. There you go. So it really makes sense. It's that same formula showing up again. This is why the mechanics of the integral are so important to make sense of. All right, now we're going to do the same thing for the moment with respect to the x-axis. Same idea, but now we're going to be measuring to the x-axis. So the distance from this point right here to the x-axis is 1/2 of x sub I bar right here, like we were talking about just a minute ago, right? Now, what is the mass of the rectangle? The mass is just the density times the area, so that's right here, right? We've got area times density gives us mass. So the moment is the mass times the distance from the x-axis. Do a little bit of algebraic massage, move things around a little bit, and we can rewrite it like so. So that gives you the moment of one of those rectangles with respect to the x-axis. That's what this formula is giving you. All right, so taking the limit as n goes to infinity, again, we generate this formula. This is the formula for the moment of the region about the x-axis, or with respect to the x-axis. And again, same kind of thing. One thing that students tend to ask, and one thing that gets a little bit lost in the formula, is where the squaring is coming from. So let me go back one more slide. The squaring is coming from this fact that to find the area, f of x sub I bar appears in that area formula. But then to find the centroid, or I should say to find the distance to the x-axis, that f of x sub I bar occurs again. So this is where we're getting the two factors of x sub I bar, and that's why we get a square in there. All right, so that's where the squaring is coming from. Okay, but that's our formula. That's our formula right there. So now altogether, we have the moment with respect to the y-axis, and we have the moment with respect to the x-axis, given by these two formulas. All right. Again, these are two formulas that you do want to memorize. You want to at least be able to recall them. I know I sound like a broken record when I say this, but this is why the mechanics of the integral are so important to understand. It's important to look at these formulas and see where every single piece is coming from. Every single piece comes from the construction of the thing that we want to integrate, right? That's the creative part. So why is there a 1/2 here? Why are there two f of x factors here? What is dx in this case? What is rho? And we're adding it all up. So you should be able to make sense of each piece of that formula. And if it doesn't, please ask me and I'll be happy to elaborate more on it when we have our meetings and go through the activities. All right? Okay, now we've got the moments. Now we're really close to finding the center of mass. So what did we need to find the center of mass? We needed the moments and we needed the total mass. So let me ask you this question before I go forward a slide. How could we find the mass of this region under the curve f of x? Think about it for a minute. Pardon me. All right, so hopefully some of you were thinking about area and finding the area under the curve, because that's exactly what we're going to do. We're going to find the area under the curve and multiply it by the density, because that'll give us the mass. But luckily, we already know how to find the area under the curve. That's the basic Riemann integral, right? So mass is density times area. The area under the curve is this integral, because now you're just adding up literally the area of the rectangles and then taking the limit as n goes to infinity. So this is the formula for the mass of the region. Now that we've got the formula for the mass, we've got the formula for the moments, formulas for the moments, we can get the formula for the centroids. So here we go. This looks messy, but it cleans up rather nicely. The x-coordinate for the centroid is, or center of mass, I should say, they coincide in this case. The x-coordinate of the center of mass is my over m. Here I'm just plugging in those formulas. Now, because our density is uniform, it actually does not factor into where the centroid is going to be, or the center of mass is going to be. So what you'll notice right here is that the densities cancel. And then we're left with this expression, which is better represented by this expression. Oops. Right here. So there's a bit of like a symbol manipulation here that I want to emphasize, but this upper integral is this integral right here, right? All I'm doing between this step and this step is I'm rewriting the area as 1 over a in the front. So a is equal to the area. That's what I'm trying to say right here. So you can think of the x coordinate of the centroid as being the moment with respect to the y-axis divided by the area, which makes sense, right? It makes sense because it's the moment divided by the mass. So there it is again. So it's the moment divided by the area because our density is uniform. Now looking down for the y coordinate of the centroid, you get something similar. So the rows here will cancel because the density is uniform in our cases. And so what you get is moment with respect to the x-axis divided by the area, which we can rewrite like so. So as messy as those look, as messy as these two formulas look, those give you the coordinates of the centroid, or the coordinates of the center of mass. That's it. So that is the center of mass, and those are the formulas for it. So putting it all together, whew, now that we've developed all the theory, here we go. Area of a region under a curve. Mass of a region under a curve is just density times the area. X coordinate of the center of mass, Y coordinate of the center of mass. All right, so these are all formulas that you need to know, that you need to have memorized, that you should be comfortable with. These two ones are the ones that are the easiest to forget, I would say. But again, they're easy to remember if you remember where each piece comes from, right? Distance from the y-axis, area, distance from the x-axis, area, and it kind of falls out from there. All right. Whew. All that being said, let's practice a little bit. So let's apply these methods. Let's find the center of mass of a semicircular plate of radius r. And this is one that I want you to try on your own, but I'm going to draw a picture just to emphasize what's going on. So I can draw a better picture than that. Here's the setup. All right. Here's a semicircle. Pretend that's a perfect circle. That's negative r, that's r. My question to you is, where is x bar, y bar? Man, my handwriting's gotten worse over the years. All right, there's what the region looks like. Maybe I'll even fill it in. So the region is this solid semicircular plate. R is fixed. R is fixed, so that is not changing. And I want you to try to figure out where the center of mass is using the formulas that we just derived, okay? So think about it for a minute. All right, now say something out loud to yourself about how you could proceed. Maybe a formula or something you could start with. All right, and now get calculating. You're going to have to compute a few integrals. So there's at least 4 integrals that you're going to need, or maybe 3, I should say 3 integrals that you're going to need. So compute those, and then we'll do it together in a minute. All right, here we go. So if I want to find the center of mass, the first thing I need to find is the mass, and then I need to find the moments, right? Or maybe I should say I need to find the area, and then I need to find the moments. So here we go. Oh yeah, there's this bit. I should have said this first. One thing I know is that our region has symmetry. It's got symmetry about the y-axis. Symmetry about the y-axis right here. Okay? So because of that, we know that our center of mass has to lie on this line somewhere. And intuitively, there's more mass near the bottom. So I suspect the center of mass will be a little bit lower. Will be a little bit lower there. Somewhere around there. And that's exactly where I would put my finger to balance the semicircle on my finger. Okay? There we go. So that's the symmetry principle. So right away, we know this. This actually, like I said earlier, cuts our work in half. So right away, we know the x coordinate has to be 0. If you didn't remember that, that's totally fine. When you compute the formula for the x coordinate, you will get 0. You will get 0. But then at the end, you're going to be like, oh yeah, that's right, there's symmetry. So I encourage you to look for symmetry. Symmetry always helps, or I should say, symmetry can help when it comes to integration. So pay attention to symmetry that could pop up. All right, now to find the y coordinate, we use the formula above. The formula was this. Now we just need to plug in all of the info that we know. The area is not so bad. The area is half the area of a circle. You should know the area of a circle is pi r squared. So the area of a semicircle is that divided by 2. And so that's what you're seeing right here, this piece right there. We also know that a function that describes the upper hemisphere here is square root of r squared, minus x squared. That's the formula for it. So that's our f of x. That's our f of x. There we go. And that's why it's coming out right here. That's f of x. Now we can simplify. So a couple nice things that I noticed right away. The 1/2s here will cancel. The square root and the square here will also cancel. And so we're left with a not too bad of an integral, actually. This is the integral we're left with. Now, just a reminder here, r is a constant. R is a constant. It is not changing. It is not a function of x. Another thing is I employed symmetry here. So notice we were integrating from negative r to r. Well, our region is symmetric about the y-axis. So we can just integrate half of it and then double the result. So we can integrate from 0 to r and then multiply it by 2. So that's where this is coming from. Integral 0 to r times 2 of this integrand, and the integrand is pretty nice. Hopefully it's I mean, you may not feel a breath of relief yet, but remember r is a constant. So when I anti-differentiate it, when I anti-differentiate r squared, I just get r squared x. And then for x squared, it's just the good old power rule. When I anti-differentiate it, I get 1/3 x cubed. And then now I can apply fundamental theorem of calculus and do some arithmetic. So evaluate at r, evaluate at 0, you get this, simplifies to this times this, which gives you this. So 4r over 3 pi, and that is where the centroid is. So altogether, that's what we've got. Let me put this right here. This is the point 0, comma 4r over 3 pi, where this is negative r and this is r. All right. Okay, not too bad, right? Not too bad. So trucking right along. Again, I know this has been a long lecture. We're nearly done. Now that we found these formulas, we can modify them a little bit to find the centroids of regions that are between two curves. So here we go. If our region R lies between two curves, y equals f of x and y equals g of x, we use the exact same arguments as before. So I'm not going to go through all the arguments again. And you get these formulas. Formula for the x-coordinate, formula for the y-coordinate, right? And the formulas should look very familiar, right? They should look very, very similar. And again, it's because we've still got x f of x and x g of x for the x-coordinate. We're just taking the difference. And then we've still got 1/2 f of x squared and 1/2 g of x squared. We're just taking the difference. That's what's going on here. All right, now that we know those two formulas, let's apply it. So let's find the centroid of the region R bounded by these two numbers. I'm sorry, new numbers, what am I saying? These two functions, y equals x cubed and y equals square root of x. And I want you to try this one on your own, all right? So let me throw up the thinker. Think about how you would start for a minute. All right, now say something out loud about how you would start. All right, and now try to work it out. Use the formulas from the previous slide. Plug in what you know about f of x, g of x. Just remember one has to be above the other, just like you did when you first learned that area between two curves. And then try to work it out. We'll do it together in a minute. All right, here we go. So again, if you can draw a picture can help. I know a picture helps me. So let me start by drawing a sketch just to see what the region looks like. Y, X, Okay, so our first curve is x cubed, which looks like this. Oops. And our second curve is square root x, which looks like this, roughly. All right, they meet at a point, and since we're looking for the region bounded by those curves, actually, I guess I should have said we're going to say x greater than or equal to 0, so maybe I'll add that afterward. They meet at the point 1, comma 1. How could I find that? If you set them equal to each other and solve, you'll see. So like x cubed equals square root x. If I square both sides, I get x to the 6th equals x. Then they meet at 0 or 1. There we go. That's one way to do it. Okay, so they meet there, and we're trying to find the centroid of this region. Okay, well, I don't think there's any vertical or horizontal symmetry. No. They're not symmetric about on any other line because these powers aren't the same. If the powers were the same, we could actually use the symmetry principle, but they're not. So in this case, we are stuck computing the coordinate of both. Yes, we'll have to compute the coordinates for both the x and the y coordinate of the center of mass. All right, so first thing we're going to need is the area. So let's find the area of the region. One thing I'll point out is that the square root function is the upper function, and the cube function is the lower one. So remember, when you find the area of these things, you do the upper minus the lower, right? So that's what this is. Now, easy integral, they're just power functions. We can use the power rule, anti-differentiate them, use FTC2, simplify, and we get 5/12. So that's the area of this region. The area of this region is 5/12, right? Now we can use the formula for the x coordinate, 1 over the area, and then it'll be x times root x minus x cubed. Go through some simplification a little bit, distribute this x, flip the 5/12, and then again, you've got a pretty basic integral. They're both power functions. Use the power rule, anti-differentiate, use fundamental theorem of calculus, and then simplify to get 12/25. Now we do the same thing for y bar. There's the area. We have 1/2 root x squared minus x cubed. Oh wait, I have a typo right here. There's a typo. This should be right. Oops, right here. There we go. That should be right there. See, did I? Okay. Yeah, okay. That's just a typo. I fixed it in the next calculation. Okay, so a couple things first. All right, so when you flip this, you'll get 12 over 5, right? 1 over 5/12 is 12 over 5. And then when we pull out this 1/2, it'll cancel with a factor of 2 in the 12, and it'll give you a 6. That's where that comes from. Then if you apply these powers, you'll get x and x to the 6th. Once again, simple power functions, anti-differentiate, FTC2, and then simplify to get 3/7. So the centroid of this region is at 12 over 25, comma 3/7. All right. Whew. Okay, trucking right along. Now, oh, you know what? I just realized. Yeah, trucking right along. Now we can talk about the theorems of Pappus. So bear with me for just a few more minutes here. We're almost done. We have the first and second theorems of Pappus, and I'll talk about them, and then I'll show you an easy animation to make sense of them. But this is the one that I wanted to mention in the last section, but I wanted to hold off until we talked about what the centroid was, what the center of mass was, how it was being computed. So the first theorem is this: the surface area of a surface of revolution generated by rotating a curve C about an axis outside of C and on the same plane is equal to the product of the arc length S of C and the distance D traveled by the geometric centroid. So what this is saying is, if you want to know the surface area, find the find the centroid of that curve, and then multiply it by the distance traveled by. I'm sorry. find the length of that curve, find the centroid of that curve, and then multiply the length by the distance traveled by that centroid. The animation will look much nicer. uh, the second theorem of Papus is saying that you get the same thing for volume. So if you want to find the volume of a solid of revolution, like you did back in Calc 1, then you basically find the area of the region and you find the centroid of that region and you multiply the area times the distance traveled by the centroid. That's really what it is. Hold on 1 second here and I'll pull up a nice animation. All right, sorry for the delay there. Let's take a look at this. So this is another animation by this guy, Lucas Vieira, and he makes really, really great animations. So I highly recommend you look him up and look up all the animations he has. He's got a ton that are great for trigonometry. But if you click on this link, if you click on this link, it'll take you to the animation that I'm about to pull up now. So let me pull it up. Here we go. Okay. And what I'm going to do is actually refresh this for a minute. So let me start over here. There we go. So this is showing how the first theorem of Papus works for three different regions. So here you're going to get the cylinder. And then here you're going to get a cone. And here you're going to get a sphere. All right? So intuitively, this is what the theorem of Papus says. If you want to know the surface area of the cylinder, it's going to be 2 pi r c, or 2 pi ac, as he calls it here. Same thing for the cone, 2 pi ac. And for the sphere, 2 pi ac, or 2 pi ac. So in the previous section, it was always 2 pi rl, 2 pi rl, 2 pi rl, right? So same thing here. Remember I took a pi rl and I re-expressed it as 2 pi half rl? That's what's going on right here. So you basically find the centroid of those things, right? There it is. And then when you spin it around the y-axis or spin it around this vertical line, you generate the surface. What is the area of that surface? In this case, it's the length of that line times the distance traveled by its centroid. Here, it's going to be, there we go. A little bit glitchy. Here, it's going to be the length of this line times the distance traveled by the centroid. And then same thing over here. I'll let it replay for just a minute before I say the rest. All right, there's the centroid of the region. And if you spin it around like this, you'll get the surface area formula. There we go. So we actually found the centroid of this region in a previous example. So if we wanted to know the surface area or the volume, we could just take that centroid and multiply it by the distance there. Or I'm sorry, take the length the length of this and multiply it by the distance traveled to get 4 pi r squared. If we wanted to find the volume, we would take the area of that semicircle and multiply it by the distance traveled by the centroid. So that's the idea. Again, I encourage you to stare at this, look at it, look at the formulas, and you'll notice that the formulas are very, very similar to what we derived in the previous section. And you could also probably see where the volume formula is going to come out of that as well. You could do the same thing for a cone, and I think I might even have you do that in the activity, so I won't reveal too many details about it. All right, let's go back to the slides, and let's use it. Let's use one of these theorems. All right, let me do this. There we go. Okay. Yeah, okay, there we go. So let's find the volume of the solid generated by rotating the region R from the previous, I don't do it here. Okay, we'll do it later, don't worry. Rotating the region R from the previous example about the y-axis. So what I'm saying is take this region, which I sketched, take this region, all right, and find the volume of the solid you get by rotating around the, did I say, y-axis by rotating around the y-axis. So we're going to go like that. Now, in Calc 1, to find that volume, you would use cylindrical shells, which we're going to do in just a minute. But with the theorem of Papus, you can do it very, very quickly if you know where the centroid is located. So we're actually going to do both approaches and compare the two. So let me go back to this. All right. So here's the cylindrical shell formula. Here's how we compute the volume with cylindrical shells. And I'm sure you had to do something like this in Calc 1 before. 1 second. There we go. Okay. So cylindrical shells. We can use a previous result to save some work. Oh, yes, because we did calculate something earlier. So here's the first bit. The height function for our shell formula is given by the difference between those two functions, root x minus x cubed. That's our height function. Now, what's the radius function? The radius function for us is just x. It's just the distance from the y-axis. There we go. Now we compute this integral and it gives us 2 pi over 5. So that gives us the volume using cylindrical shells. By the way, this cylindrical shell formula hopefully maybe looks a little bit familiar to you now because it's 2 pi RH, 2 pi RH. Cylindrical shells because it's 2 pi RH. Okay, now let's use the theorem of Papus. So we found that the centroid of the region was 12 over 25, 3/7. So the theorem of Papus says multiply, or basically find the distance traveled by that centroid and multiply it by the area of the region. All right, so since we're rotating it around the y-axis, the radius of the circle is going to be 12 over 25, because that's the distance from the centroid to the y-axis, right? Now the area of the region is 5/12, which we calculated earlier. So the volume is going to be 5/12 times 2 pi r, which is 2 pi times 12 over 25, which is 2 pi over 5. All right. So that can be handy. That can be handy if you have some of that information. So there's more than one way to do that. But on that note, let's play. Whew. So I'll try to keep this short. All I can say is that with these application sections, there's really lots to cover. There's a lot of theory to derive. I like to emphasize the theory a bit more. As far as applications and using them, you're going to use them so much in your major courses. You'll see what I mean. So if you understand the theory deeply, that's a good place to start. Understand the theory deeply, and then you'll apply it in your major courses. All right? If you have questions, you can always ask me. And until then, I'll see you next time. Bye-bye.